Welcome to Day 6, Growth and Decay Applications. You will need the 3 Ps as well as a graphing calculator. Today we will practice a little bit more with the growth-decay formula we learned in the previous lesson. This formula is very versatile as it has consequences in finance, business, chemistry, biology, physics, and even sociology. Remember that this formula can be thought of as a function of time, t, and that when necessary in the calculator, a of t will be the y value and t will be the x value. Also remember that to model these problems, you must be able to identify the individual parts as shown from the information given. Also, once you identify a problem as growth or decay, it will be helpful to write this equation right away. Make sure to pause the video and read the problems before proceeding in order to understand the descriptions. In example 1, we're given a problem that describes a population of wolves in a year that is decreasing at a given rate. What we should notice is that this is a decay problem by noticing the key phrases declining at a rate over time. Once you identify this, you should write the formula for decay, noticing that the sign between 1 and r is minus because we are declining or decaying. Now, to write an equation to represent the situation, we have to pick out the pieces of information that correspond to the variables in this formula. Here, the initial value a is stated to be 35 million. So, we can substitute in 35 for a. Note, I could enter in the whole number, 35, with all of the zeros at the end, but for shorthand purposes, I will consider the million to be a unit for now and include it with the final answer. Next, looking at the rate of decay, I see the value given is 4.3%. So, I plug this in for r in decimal form, remembering to subtract it from 1 because, once again, we are declining or decaying. So my rate of decay should be negative, in this case negative 0.043. Finally, to generalize this function for the situation, I leave t and a of t alone, as we are not being asked to solve for a value yet, but merely to model the situation. So here I'm going to bring down a of t on the left and bring down t as the exponent of the decay factor on the right. Once I've simplified the decay factor, I should be left with a function of t that models the problem and can be used to predict specific situations given the information or given new information in the future. For b, we simply need to know the parts of our formula. When we are asked what is the decay factor, we know that this is the part of the formula that involves the rate. In other words, 9.57, or rather 0.957, is the decay rate. In part C and D, we will utilize the function that we've just written to analyze what happens at very specific conditions given this model. In part C, we want to determine a final value of the population of wolves at a very specific point in time, i.e. the year 2000. However, t is the time that passes, not the year. To determine the time that passes, or the variable t, we must use the base year of when the initial population A was measured, in this case 1985, and subtract it from the year 2000 to find that the time that has passed t is equal to 15 years. Now, like any other function, we want to find the value, our final value, a of t, at t equal to 15. So what we're looking for is a of 15. And what we do is say it's equal to 35 times our decay rate, 0.957, and t we substitute in 15 for the years. When we plug this into a calculator, we should come out to 18.1 when we round to the nearest tenth. So we can say 18.1 million wolves will be left in the year 2000. In Part D, we are asked to find in what year the population reaches 13 million. In other words, we are looking for a value of t when the final value is given. To solve this by hand would take a lot of manipulation, but luckily, we can solve it much easier using the table function in our calculators. Start this problem by rewriting your equation with y and x taking the place of a and t respectively. So here I'm going to rewrite my formula for this situation. Now I am rewriting it where y takes the place of a of t and x takes the place of t in the formula. Next, using the y equals application on your calculator, you want to enter the equation as shown. So here I'm going to, for y1, plug in 35 times 0.957 raised to the exponent x. Now, I'm going to use the table function by hitting second table to get a list of x and y values for the function. Scrolling down shows you that after 22 years, we are slightly over the 13 million mark, but by the end of the year 23, we have dropped below that 13 million mark. So we can conclude that somewhere in year 23, the population will decrease to the level we're looking for. However, this just tells us the years that pass. In other words, t is equal to 23. To know the specific year that it will occur, we need to add this value, t, to our base year. Because the base year is 1985, we add 23 years to that and find that the population reaches 13 million in 2008. For example 2, pause the video and see if you can complete the problem on your own on a separate sheet of paper. Begin the video again when you have completed all parts and check your answers against what is shown. How did you do? The first thing you should have recognized about this problem is that it is an exponential growth model based on the keywords that you see within the problem. Here, you see increase and at a rate. So you should instantaneously recognize this as an exponential growth problem. Remember, once you recognize an exponential growth or decay situation, you should start by writing the general formula, and in this case, we're going to use 1 plus r because we are growing the initial amount. We're not decaying the initial amount. So our rate will be positive. Next, to write an equation modeling this specific situation, we need to plug in the information that is given for the variables. Here, the initial amount that Eric invests is $2,500, so we substitute in $2,500 for little a. The rate of increase we know is given as 6.35% each year. So for little r, we're going to plug in the decimal value of that 6.35%, in other words, 0.0635. And once again, we know that t is in years. However, we're not asked to solve, merely to model. So we're going to leave a of t and the variable t alone within the situation. Once we have simplified our growth factor, we should be left with a generalized function for this situation that will let us solve for more specific parameters in part B and C. In B, we are given a base year and asked to find a final value in a given year. In other words, we want to find an a of t at a given t. Remember that t, or time, is not a given year, but rather is the time that has passed on from the base year to whatever year we're given the scale of t, in this case years. To find the time that has elapsed, we subtract the base year from the final year that we're given to see that 13 years will have passed between 2007 and 1994. We now plug the value of 13 in for t to our function. In other words, we're looking for a of 13. We keep our initial rate 2,500 and our growth factor 1.0635 and raise that to the year 13, or rather the times that have passed, 13 years. If we use a calculator and we plug everything in correctly, we should find that Eric's money, if he leaves it alone and does nothing else to it, should, in 2007, be equal to a value of $5,565.80 when you round to the nearest cent, as most financial institutions do. In C, we are once again asked to find a year when a final value will be reached. In other words, we're looking to find a time t given a final value a of t. Once again, when you have a problem where you're looking for the time, it is much easier to use the table function in your calculator than to do the manipulation. So, in order to do this, we need to rewrite our function for this specific situation. In other words, a of t equal to 2,500 times our growth factor, 1.0635 to the 13, or rather to the t, and we need to substitute in for a of t and t with y and x, as shown. Now, once you have your rewritten formula, go into your calculator and use the y equals application. Enter in the rewritten function with your x value as shown, and then hit second table to get a list of x and y values for the function. Now you're going to scroll down until you reach a point where the y value crosses the threshold that we're looking for, in this case 24,000. You should note that this occurs when the x value, in other words the time in years, is at 37. Notice that 36 is not quite there, but 37 years is over. So we know that the money reaches the value of 24,000 in year 37. Once again, this 37 is not the year that we're looking for, merely the time that has passed. In order to find the year, we need to add this 37 years to our base year that was given, in other words, 1994. So 37 years after 1994, his investment will reach 24,000. If you put this together, that means his money will be worth $24,000 in the year 2031 or 2031. A variant of the growth formula is the compound interest formula. This formula is used by investment firms, finance, and lending businesses when interest is added to an account multiple times a year. In other words, the interest is compounded. This can occur semi-annually, or twice a year, quarterly, or 4 times a year, or even monthly, which gives you 12 times a year. The number of times the interest compounds is reflected in the variable n, which divides r and is multiplied to the power of t. It is determined by one of the keywords, semi-annual, quarterly, monthly, etc. A problem involving a problem that will utilize this formula will always have some variant of the word compounded in it. So it might be compounding interest, or compounds, or it compounded over time. In example 3, after reading through the problem, I noticed the keyword interest and compounded, which should tell me this is a compound interest problem. As such, I start by writing the general formula. As shown. Similarly to the previous examples, I will now identify the pieces of information that correspond to each of the variables and subsequently plug them in to get a function that expresses the example. The initial amount invested, A, is stated to be $2,700. The rate of interest is 9.2%, So I plug it into the formula for R in its decimal value. In other words, I'm going to substitute in for R 0.092. Next, I look for the key word that tells me how many times in a year the interest is going to be compounded. As it says quarterly, I know that the value of n will be 4 because the interest is compounded 4 times over that year. I plug in this 4 for n underneath both my rate and outside the parentheses as a multiplier of t. Setting the whole statement equal to a of t gives me a function for this example, which I can now use to find out details about the specific situation. I'm also going to simplify what is inside the parentheses to give me my final growth factor. Here, once you simplify the fraction, you can use your calculator to do so. You should get 1.023, and once again I'm going to raise this to the 4t. So now I have my general formula for this situation. The question is asking me to solve for a final value, a of t, in the year 2002. So in order to do this, I need to find a value for t. I do this once again by subtracting the base year given to us, in other words 1995, from the final value year 2002. This allows me to get a value for t of 7 years, which I subsequently can plug into my formula. And I'm just using function notation here. A at t equal to 7 is equal to 2700 times 1.023 raised to the 4 times 7. You don't necessarily have to simplify it, but I have here. And if you plug everything into your calculator correctly, you should get a final value of $5,103.66 is the amount that Jonah will have in 2002, assuming he leaves his money alone. So here are the things you should be able to do. If you're struggling with any of these, go back and rewatch the video focusing on the skill that you feel that you're struggling with. Until next time, this is Mr. Mackman signing off.